Hello, everyone. Thank you for joining me in this set of slides related to FNTech 101. What we'll be discussing today is the IT infrastructure and the new advancements that are happening in the technology and how it impacts our life in terms of AI in general. This particular set of slides is not specifically talking about finance, but it's addressing the technology aspect. So let me share the screen and we'll go through the set of slides like we normally do. What we'll be discussing today is what IT infrastructure is, what are the drivers for IT infrastructure, the components of IT infrastructure. We'll talk about contemporary hardware trends and software trends, and we'll talk about infrastructure management issues, and finally we'll end with artificial intelligence. In here, there's a slide that shows us what the future is holding for us. What you're expected to do is to watch that particular video and then determine what specific aspects in there you expect them to happen and which specific aspects are a little bit off. At the bottom of the slides, in the notes, there's another video that you need to watch as well that also talks about the history of the future. And you need to do the same thing with that other video as well. IT infrastructure in general is the technology that helps the company manage its information systems. The components of it include the hardware, the software, the services, and the cost of IT infrastructure is massive. We're talking here about $1 trillion for the hardware and software, and another $1 trillion for the services associated with IT infrastructure. There's a video behind that that talks about IT infrastructure in detail, and you're expected to watch that video. So in here, we're talking about the client-server architecture. And the client-server architecture, the key aspect of it is that there's a server that does the huge amount of the heavy lifting, but the client as well does lots of processing in there. So the client-server architecture is an architecture that started in the 80s, and actually it is carrying forward with us up to today. The internet, realistically, is nothing short of a client-server architecture where the web server is the server, although it might have different tiers in there, but it is a server in there. And then we have the browser that represents a client. The client in such a situation does not do a lot of heavy lifting, it does a lot of processing. Most of the processing is done on the server side, but the client just takes the HTML code and renders it on the screen. Sometimes it does some processing related to JavaScript, but most of the time, the heavy lifting is done on the server side. The other type of architecture that started in the 90s is the multi-tier architecture. And the multi-tier architecture looks at different areas, different tiers in the infrastructure altogether, from the client until the data. So you can see in here that the data is considered one tier, the application server is another tier, and the web server is a third tier. And you can have multiple tiers in there without any problem. Again, this one also has a video. The previous slide also had a video in there about the client-server architecture. And the advantages of that include that it has a better security, better scalability, simpler maintenance, easier enhancements. And these are all explained in detail in the video that we have in here. We'll talk about APIs later, but APIs are application programmer interface. And these are basically functions that are called from another computer and they go directly against application server. I will not play that video right now, actually. The testing is much easier with this one, and the deployment of new code can be much easier as well because you don't have to deploy in all the tiers at the same time. You can deploy something on the client or on the web server, at the application server and data server without impacting the other tiers. Although you have to remember that usually the changes on the database gets propagated to all the other tiers as well. But the changes on the web server in the rendering of the HTML code does not necessarily require changes in the application server or the database. The next slide talks about what the cloud is. And the cloud is basically, it's called the cloud, but it's the reason that it's called the cloud because the location of the data that you have is unknown. When you look at the cloud is here right now, but it could be there next day. It could be the other place in somewhere else, wherever we want. We don't know where the cloud is. And that's the same thing with the data when you have an application running on the cloud. When we're talking about the cloud, we have three different types of cloud applications. There's software as a service, there's infrastructure as a service, and there's platform as a service. And if you look at the video in here, it will explain what the cloud is at a very high level. That's an older video in here about the cloud, but in general, what you need to do is to search for newer videos about the cloud, and then you'll have a better understanding of what it is. In general, as a simple thing, when you're talking about an application that's on the cloud, that means it's running on a server that you don't know where the location of that server is. But you have the IP address of it, but you don't know actually where the location of the server. You can always find out the location of the server when you talk to your internet service provider, or you can do some searching and find out the exact location of the IP address. But in general, that location can potentially change from one time to another. The next point that we want to discuss in here is Moore's law. And Gordon Moore came up with that law in 1965, where he said that the amount of processing or the amount of transistors that we can put on a millimeter will be doubling every 2 years. Later, that was adjusted to be doubling every 18 months. And basically, what it is telling us that for the same dollar, the power of the computer will be doubling every 18 months. He was talking only about the speed of the computer and the processing power of it. He did not talk about the enhancements on the network side or on the data storage side, which we'll be discussing later. That particular prediction that he had, he expected it to continue for 10 years, but actually continued for 55 years. And up till now, it is moving in a strong manner. And actually, when we go to quantum computing, you'll find out that it will still continue operating at this particular speed. And this law is not expected to end anytime soon. You can always go and look at Gordon Moore, who was one of the founders of Intel, 1965. That's when he came up with this one. He's an electronic engineer. And he expected it only to last for 10 years, but it lasted for a long time. It lasted for over 50 years. And then there's another video in here that talks about Moore's law. Moore's law actually is not dying. Some people are predicting that it's dying, but in reality, it is not dying. And the reason for that is that new types of computing is coming up, like neuromorphic computing and quantum computing and the likes, in addition to the enhancements that are happening related to the network and to the data storage. There's a video in here that talks about whether Moore's law is dead or not, and you're expected to be watching that particular video. In the notes, there's another video as well that you're expected to watch it. And it also talks about whether Moore's law is dead or not. The next thing that I'd like to talk about is neuromorphic computing. And there are a few videos in here that you're expected to watch. But in general, neuromorphic computers are computers that have linked together the data and the processing in the same place. So the data and the processing are happening in the same place. The leader of neuromorphic computer is Intel, and they have a chip called Louis, and there's a few links in there that talk about Louis. And the reason for that is that when we are trying to write software that tries to mimic the human brain, we are facing a challenge with the existing architecture, where the processing is done in the central processing unit, and the data is stored either on the RAM, where it's temporary data, or on the disks or the EPROMs, addressable programmable read-only memories, or the solid-state disks, or regular disks or CDs for the data storage. So the processing and data storage are separate. They are done in different places. And that results in lots of communication between the RAM and the CPU, and that slows down the processing quite a lot. However, when you put the data and you put the processing in the same place, like the human brain is operating, because the human brain has neural cells, and the neural cells that we have in there on our brain, billions of neural cells, each one of them stores data and processes the data at the same time. So it could be storing the data and processing the data. Not only that, but the processing of the data helps in modifying the data, and that's basically where the learning happens in our brain, or creates new neural networks and so on. You're expected to watch these 3 videos that talk about neuromorphic computing, and actually they are quite interesting, and you'll be surprised how effective it would be in helping us writing efficient and fast artificial intelligence programs. We'll be talking about AI a little bit later. That takes us to quantum computing. Quantum computing is a very simple principle. Quantum computing talks about the 2 basic principles of quantum mechanics, which are entanglement and superpositioning. Superpositioning means that the particle we know that it is somewhere, but we don't know exactly where it is. So it can assume any particular location, can assume any type of rotation, could be rotating clockwise or anti-clockwise. There is a percentage possibility that it could be rotating clockwise or anti-clockwise, but we don't know exactly until we observe it. Until we observe it. And our observation will force the location or the rotation of the particle that we have. That's called superpositioning, because at the same time, it would be either positive or negative. And it could be positive and negative at the same time. So someone will think, what does this mean? And Schrodinger tried to give an example. He gave an example jokingly, but this example picked up quite nicely. That if you put a cat in a box and then put beside the cat a canister, and this canister, we don't know what it has. It could have a perfume or it could have a poison. And you break the canister. Then the cat will either be very happy about the aroma of the perfume, or will be dead because of the poison gas that you'll receive. Until we open the box, we don't know what's the situation of the cat until we open the box. And it could be that the cat is dead, or it could be alive. And actually the status of the cat, that it is 50% dead and 50% alive. So the cat is practically both dead and alive at the same time. And our opening the box forces the position, and we find out whether it is dead or alive. So you'll see in here that opening the box and whether the cat is dead or alive are two different events, and these events are entangled with each other. If the cat is dead and we open the box, we'll realize that it is dead. If the cat is alive and we open the box, we'll realize that it's alive. And these two events are very much entangled with each other. The entanglement also shows itself in other types of tests in quantum mechanics, where you can have a particle that's rotating clockwise and another particle not at a close proximity. Practically, it could be galaxies away. But as long as these two particles are entangled, and there are mathematical proofs associated with that, as long as these two particles are entangled, when a particle rotates in one direction and it changes its rotation, the other particle will change its rotation as well. That concept of entanglement will make you think, well, can we actually use that particular entanglement to communicate in a speed faster than the speed of light? And the answer for that is no. Because once we check and observe the rotation or the status of one of the particles, this entanglement is lost immediately. This entanglement is immediately lost, and you cannot check it another time. And as a result of that, trying to use that particular principle for communicating faster than the speed of light is a futile exercise, and it would not work. More about quantum computing. What we have basically in regular computing, we have bits. In quantum computers, we have something called qubits. These qubits can assume a position of either 0 and 1 at the same time. And these qubits that we create in a quantum processor different qubits could be entangled with each other. So the change of one would result in changing the other. These two principles would result in creating something for us called quantum computers. And quantum computers, it's not that they are a replacement of the existing computers, because the only thing that they can do, because of the nature of the qubits in there, they can come up with all the answers to a problem at the same time. Then what we need to do is to use a regular computer to eliminate the answers that do not make sense, and whatever remains is the proper answer for the question. And the method of eliminating these answers that are not correct is something called Grover algorithm. So the Grover algorithm is what eliminates these particular answers that are not correct. Again, another time, there are 3 videos in here that you're expected to watch. The most important one is a Google breakthrough. And then at the bottom of the slides, there are a little bit more videos that you might like to watch as well about quantum computing. The open book questions at the end of the slides today are related to quantum computing. That takes us to data storage. And this is an old video that talks about data storage. And there are many areas in data storage, including hammers and including helium drives, solid state disks. But some of the more interesting storage technologies that are coming up are the DNA storage, where you store the data on DNA, synthetic DNA. And that technology is here today and now. And within 1 cubic centimeter of DNA, you can store petabytes of data, thousands of terabytes of data in 1 cubic centimeter of synthetic DNA. It's just an amazing technology. And what you need to do is to watch that video and then go to the bottom of the slides. And there are 4 other videos that you can watch as well that talk about different types of data storage. The next point that we discussed today was Metcalfe law and network effects. And network effects actually are a very interesting concept. And they indicate at a very high level that network effects happen when the value of an enterprise increases by the increase of the number of users. So, of course, when we have 2 users, there's 1 connection between them. You cannot have more than 1 connection between them. When there are 3 users, there are 3 connections. When there are 4 users, there are 8 connections, and so on. And the number increases almost geometrically, n to the power of 2. That's basically what it is, approximately. N to the power of 2 over 2 divided minus n. That's basically what it is, minus n over 2. Or n times n minus 1 over 2. That's basically the formula for Metcalfe law or the network effects. If you graph it, you'll find out that it works basically like, it's not exponential, it's a geometric graph similar to a parabola. There are certain definitions that you need to know. The network effect, we have just talked about it. That's also called network externalities. And it tells you that the business value grows with the growth of the number of users. There are switching costs, and the switching cost basically is the cost that people have by leaving a platform that has network effects. The platform is what the people are using. For example, if you look at Facebook, everyone's using Facebook. It has network effects. Leaving Facebook and using another social network is not such an easy thing, and there's a cost for switching. And how do you switch? That's a different issue. So the primary sources of value for network effects is the exchange. What are people actually exchanging? So when you think about YouTube or Facebook, they're exchanging pieces of information or they're exchanging videos. They're staying power. And basically what we're talking about in here is, would people stay with this particular platform that we have, even though there might be a superior platform? And you'll find out that, yes, that's what people would do. For example, QuickBooks is not the best platform that are out there. But if you know about it and you know that all your clients are using QuickBooks and so on, it doesn't make sense for you to move to another platform. And then there are complementary benefits. So you'll see in here, for example, if you're looking at Zoom, for example, that we are using, that I'm recording on right now, you'll find out that Zoom provides cloud storage. That means that you can store your data on the cloud. And these 3 sources of value for the network effect work together. So how can figure out these values? We have to ask questions. So when we're talking about the exchange, we need to ask what exactly is being exchanged. And can this item be replaced? What is being exchanged? Can we replace it or not? If we're talking about staying power, we need to ask ourselves, what are the components of switching costs? So if we want to switch, why would people have a cost associated with switching? And if there's an inferior technology in an existing network, is it worthwhile trying to improve the technology to catch up with the competitors that do not have the network effects or not? And for the complementary benefits, you need to identify, first of all, what's a primary product, and then identify what the complementary benefits on top of it are. There are different types of network effects. The most important categorization is whether it's one-sided or two-sided network effect. In a one-sided network effect, we have only one type of customers. For example, we have Facebook, and it has only one type of people who are using Facebook. I'm not talking about Facebook Marketplace. Facebook Marketplace will be considered a two-sided market effect because there are the sellers, that's one type of users, and there are the buyers, who's another type of user. So the same platform can have both one-sided market effect and two-sided market effect. Another example of two-sided market effect would be any type of marketplace, whether it's Amazon or Facebook. Uber would be considered a two-sided market effect as well. And there's an exercise in here. We need to find out 3 examples of one-sided market effect and 3 examples of two-sided market effects. And another thing that I'd like to think about, where can we find a 3-sided network effect? Think about that for a moment, and then we can discuss that later. But think about it a moment, pause the video, and think about where can you get a three-sided market effect, which is a market effect, and there are three types of customers, and each one of these customers benefits from the increase of the other customers that are out there. And an example of that would be Uber Eats. Uber Eats has the eaters, this end customer, who are eating, who are ordering the food. There are the drivers, and there are the restaurants. And each one of them benefits from the increase of the other two. The restaurants benefit from the increase of the eaters and the drivers. And the eaters benefit from the increase of drivers and restaurants. And the drivers benefit from the increase of the eaters and the restaurants. There are two examples in here. One of them is Facebook, and there's a long video associated with that, around 6 minutes. And there's Uber, just a couple of minutes, that talks about that. The next point is the cost of internet communication. And you know that right now, the cost of internet communication is almost non-existent. But just imagine that early in the century, the cost of 1 gigabyte communication, 1 gigabyte bandwidth, was approximately $1,000 per month. You'd pay $1,000 per month to get the bandwidth of 1 gigabyte. So you can imagine how, for communicating 1 gigabyte across internet. It's not the speed of 1 gigabyte, 1 gigabits per second. It's communicating 1 gigabyte across internet. It would cost you approximately $1,000. That was expensive. That was really expensive. But obviously right now the cost is almost zero. The next point that we have is virtualization. And in virtualization, actually, you have one single machine, a big machine, and this machine can have multiple operating systems associated with it. There's a very nice video in here that explains the virtualization in more detail, and you're expected to play that particular video. That takes us to grid computing. What is grid computing? Grid computing is the ability of using the processing power of the machines that are not being used for solving some very complex mathematical calculations. The example in here in this video is about CERN and the Large Hadron Collider, which accelerates the speed of certain particles, specifically protons, to a speed equal to approximately 0.9999 the speed of light. And getting these particles to collide with each other, creating new particles, and studying the data that is generated out of that particular collision. The Large Hadron Collider is one of the biggest achievements of the human race. When you think about the difficulty of getting the particles to accelerate at a speed very close to the speed of light, is something that's just very, very powerful about how the humans did something like this. You're expected to watch that video and search more about grid computing. At the bottom, there are two videos about the Large Hadron Collider that you're expected to watch as well. Gartner comes up with technology trends every year. And this year, these are the different technology trends in here. There's a video behind it that explains each one of them a little bit in more detail. Then that takes us to what is happening with the software. And one of the key things that is happening with software is that right now, the open source movement has moved quite a lot. As you can see in here, these are all versions of the Linux operating system. Each one of them has its own set of applications on top of it. Linux is a very interesting operating system that was created on Unix. It has its origins based on Unix. Linus Torvalds is the person who created that particular kernel of that operating system and made the source code of it available for anyone to download and compile. This particular concept of open source software is making major changes in the way that software is being operated right now. What you need to do is to watch that video in here and think about what is the future of the open source software. The video in here is a good one that explains Linux open source software in a very nice way. Then that takes us to the API, Application Programmer Interface. And that's a set of functions or subroutines or procedures or protocols that allow different computers to communicate with each other. And you can imagine the power of a computer on its own could be quite big. But once you have multiple computers communicating with each other, the power actually doubles in an amazing manner. It's as if we're having some sort of network effects related to the computers that are communicating with each other. The web services is one of the most popular methods of API. Most of the people who are using APIs right now are using web services. But what you need to do is to play the video about what APIs are, first of all, and then play the video about web services in here, which is a specific type of APIs. In here, there was an open book question. And this open book question talks about what you would do to ensure that we don't have a problem with robotics specifically and AI. How can we ensure that AI maintains its morality going forward? Before you look at the answer at the bottom of the slides for that particular question, what I need you to do is to try to answer it yourself. If you're the chairman of that Supreme Council of Planet Earth, what would you suggest that we do to this world to ensure that AI remains in check and that morally it would be acceptable to interact with the human beings? Again, the answers are down in the notes, but try to do it yourself as well. And that takes us to the part where we start talking about AI, artificial intelligence. And artificial intelligence is practically whatever you do that tries to mimic the operation of a human being is considered artificial intelligence. Now, if what you build is learning from the experiences that it had, then that's what we call machine learning. Deep learning is when it is learning, but not from just the experience that it had in the past, but learning from the new data that's given to them. For an example of that, you give the computer 1,000 pictures and tell them categorize them. You don't tell them how many categories they are and so on. And the computer is able to put the lions in one category, the cats in another category, the wolves in a third category, and the dogs in a fourth category. That would be considered deep learning, which is basically the computer is acting on its own, unsupervised by the user to come up with answers to some challenging questions. There are different types of deep learning, and if you watch that video, you'll have a better understanding of the relationship between AI, ML, and DL, artificial intelligence, machine learning, and deep learning. This video in here that you're expected to watch as well is a video that tells us whether AI is really dangerous or it's benign. And when you look at this video and review it, you'll find out that AI can potentially be very benign for us, but at the same time, it can potentially be very dangerous. The video starts by talking about the deep fakes and how deep fakes have started and the dangers that are happening in there. One of the problems that we're facing right now is that when we watch someone saying something and that thing is weird, we don't know whether that thing that we are watching is done through a deep fake or that person actually said what they said. And trying to figure that out is very, very difficult. So that's something that you need to think about, how the computer is operating and how AI can be damaging and how can it be a blessing for us. There are different areas of artificial intelligence. The first one is pattern recognition, where the computer can recognize certain patterns and predict the future based on that. For example, weather forecasting uses AI, volcano and earthquake forecasting. It uses AI as well. From small tremors, it can assess whether we have the big one or not. One way of pattern recognition is natural language processing, which is basically listening to the language, listening to someone speaking, and taking it and transcribing it, and then potentially translating it even. For example, one of the things that are happening with Zoom right now is that they are creating a system where I could be speaking in English, and at your choice, you can see what I'm saying transcribed in Chinese or in French or any other language, as a matter of fact. That's basically what natural language processing is all about. And this software is readily available right now. Maybe it's not available in Zoom, but it's actually available. When you look at the subtitles for any movie, don't expect that someone actually will be writing them. These are generated dynamically by computer software. The computer is able as well to perceive things that the humans cannot perceive, whether it's sound, whether it's vision. The computer can see a spectrum much bigger than us, can hear a spectrum of voice much bigger than us. It can actually sense very light pressure and very high pressure as well. It can sense very high, very low variations in the temperature. It can smell things that we cannot smell, for example, carbon monoxide. We cannot smell it, the computer can smell it. The sensors can smell it. And when you think about it, really, the computer can do all the things that we can do, all the 5 senses that we have, the computer can have them as well. Robotics, you need to watch that video in here because there are some very interesting things that are happening in robotics right now. And I would strongly suggest that you just go and search for the word Atlas dancing and watch that particular video if you have not watched it. Go to YouTube and search for Atlas dancing and see how the robots can actually dance, maybe as well as human beings, as a matter of fact. The system can do, computers can do planning as well. They can create project plans if you want them to. There are certain expert systems that can do only one thing. For example, play Go, or play chess, or can plan for a war, something like this. So these are expert systems that can do very specific things, or can do manufacturing, or can weld things, and so on. These are expert systems that can do specific things, and they do only one thing. People are even using computers and artificial intelligence for proving mathematical formulas, which is quite amazing. Computers are very good in game playing. And what you need to do is to see how the computer is capable of learning how to play games without any preconceived rules about how the game is being played. And an example of that is what DeepMind has done, where it threw 4 artificial intelligence players, and didn't give them any rules, not even how to walk, and give them the rule of soccer and the rewards of they score a goal in one side or the other. And all of a sudden, we found that these particular players are able to dribble, are able to score goals, and are able to play soccer after just a few days of getting these players to play on their own. Again, that is shown in detail in this video that we have in here. So where do we see AI applications? We see it almost everywhere. You see it in Siri, in Alexa, in Google Assistant. We see it in self-driving. Tesla is a leader in that particular area. We see it in X-rays and MRI, where the computer is better than humans in looking at X-rays and deciphering them and determining whether someone is sick or not. And they can see things that the humans cannot see. Even when you go to McDonald's in the United States, you'll find out that the menu for the drive-through is dependent on the time of the day, the number of people in the car, the type of the car that you have, and so on. And the license plate, even if you've ordered before, it will know what you've ordered and show you certain things and so on. So it's a very interesting technology that they have right now for drive-through, and it's based on artificial intelligence. Amazon is using it a lot when you're purchasing things in Amazon Prime Video, in AWS. So it's using it quite a lot. Netflix is using it as well. So when you watch something, it can tell you based on its recommendation, can show you something else. There is also right now funds, exchange-traded funds and mutual funds, not mutual funds, exchange-traded funds that are managed strictly by artificial intelligence. Artificial intelligence is the one that does stock selection and makes a decision to buy and sell. And these AI-powered ETFs are actually operating and getting a higher return on investment than human-powered ETFs. Google YouTube is doing some amazing things. Nest Hub, and there's a video in here that shows you how the Nest Hub can manage your whole house altogether. One of the most interesting things that's happening is neuroprosthetics, where it can manage the movements using artificial intelligence, and not only that, but can transfer the feeling of pressure, texture, and heat from the prosthetic arms into the human brain. And that's basically turning us not to be robotics or having robotic arms. It's turning human beings to be cyborgs, which they have feelings. Cyborgs, the definition, they have feelings from their prosthetic arms. What I'd like you to look as well is this video that talks about Neuralink. Neuralink is a new business that Elon Musk has created to put a chip in your brain. And this chip is capable of learning of recognizing the signals from the brain. And based on these signals, communicating it through Bluetooth to another computer. And that will be sending signals to, for example, if someone is paraplegic and has a severance, his spinal cord is severed, it will send a signal to the remaining part of the spinal cord. and get them to start moving. It's an amazing technology. Just take a look at it and you'll find out some interesting things. I did not talk about military training, but AI is used extensively in the military. And I would say that the military potentially is the bigger user of AI in the world, the biggest user of AI in the world. There are three different types of AI. There is narrow artificial intelligence or artificial narrow intelligence, which is what we have right now. There's specialized AI that's specialized in one single area. For example, AlphaGo that beat the world champion in Go. That's an example of that. Then there is artificial general intelligence, which is strong AI. That's where the computer is capable of doing everything that a human can do. An example, the closest example of that is IBM Watson. There is no current mature AGI, but Google is getting very closer to that. And when you watch the videos that you've had before about Google, you'll understand where they're coming in there. And once the computer reaches the artificial general intelligence, through its intelligence and its capability and of learning from existing data, within a few days, it will be reaching artificial superintelligence, where the IQ could be hundreds of times faster or stronger than the IQ of a normal human being. This is only known in science fiction, The Matrix and Terminator and so on, but people are expecting that super artificial intelligence will start after we reach the point called singularity. And the singularity is expected to happen between 2040 and 2050. So it will most likely happen in your lifetime, that the computer will be smarter than the human being. What will be the result of that? That is something that you can look at it through that particular video. This is a very interesting video that talks about more of a sinister, dystopic view of the world, but it also talks about the positive things that could happen through AI. It's very interesting what people are thinking about AI and whether the reality will conform to the prediction that people have or not. That's a very interesting video, and that's the last video of this particular slide that we have. You'll notice that these slides have lots of videos in here. You will need to take your time watching them, because that's what we spent in the class, and after every video we had a basic discussion about this particular video. But you need to think about it and look at each video with a grain of salt. There are lots of videos at the bottom that talk about the details of these particular topics, and you'll find lots of videos in the notes of the slides as well that you're expected to watch at the same time. So the open book question is about quantum computing, and you're expected to identify 4 generic applications of quantum computing and how regular computing would not be suitable for this application. You need to provide also a YouTube video up to 10 minutes for each of these applications. This is an assignment that's done by 4 members of the group per group. And that's basically the end of the slides for us today. So I hope you enjoyed it, and I am actually looking forward to the next set of slides, which will be talking specifically about the disruptive technology and the industrial revolution, the 4th industrial revolution. It will be a small set of slides that we'll have to cover. Thank you very much again, and I will talk to you later. Bye-bye.